In this part of the lecture, we're going to quickly cover a little bit of theory. We won't be deriving and proving any theorems, so if you're a big math buff, then check out the references section. The hash table implementation that we covered was simple to implement. It has the advantage that it doesn't really require any pointers to implement. In addition to being simple, open addressing hash tables have the potential for better performance during key lookups than a pointer-based hash table, because there's no overhead related to storing and following pointers. Additionally, this open addressing implementation could be more memory efficient compared to a chaining implementation if the hash records take up less memory than the pointers used in a chaining hash table and the percentage of occupied buckets isn't too low. Otherwise, we'd have a hash table that uses allocated memory but is almost empty. One disadvantage of open addressing hash tables is that they aren't well suited for the deletion operation. If you need to support the ability to remove a key and its associated record, then a chaining solution is preferred. We can describe how full a hash table is by calculating its load factor. The load factor is defined as alpha, and alpha is equal to n over m, where n is the number of occupied buckets and m is the total number of buckets. In an open addressing hash table, n is less than or equal to m and alpha is less than or equal to 1. This means that we can't store more records than there are buckets. We can use alpha to describe how many buckets on average will be probed when searching for a key. The following equations assume that our hash function does a good job of distributing keys uniformly in the hash table. In an unsuccessful member operation, that is when the key isn't found in the hash table, we can expect the average number of buckets probed to be 1 over 1 minus alpha. Suppose that the hash table is half full, then alpha is equal to 0.5, and we can expect to probe on average no more than 1 over 1 minus 0.5, which is equal to 2 buckets. Notice that both an unsuccessful member operation and insertion operation go through the same probing sequence, except that the insertion operation inserts a new record at the end of its sequence. Thus, both the insertion and member operations can be described with the same expression. The average number of bucket probes for an insertion operation is then 1 over 1 minus alpha. We can also describe a successful member operation. Say that the target key is in the hash table. Then the number of buckets that will be probed on average is no more than 1 over alpha times the natural log of 1 over 1 minus alpha. For example, if the hash table is half full, then a successful member operation probes at most 1.387 buckets. Notice what happens as the load factor alpha approaches 1. As the load factor approaches 1, the average number of bucket probes increases dramatically. This leads to another advantage that chaining hash tables have over open addressing hash tables. The performance of a chaining hash table degrades linearly as the load factor approaches and surpasses 1. Depending on your performance needs, once the load factor for your hash table gets too large, then it might be a good idea to add more buckets to the hash table. A simple way of doing this is to allocate a hash table and reinsert the hash records into the new hash table. Although this might sound like an expensive operation, eventually it will be more efficient than continuing to use an overloaded hash table. That's it for this introduction to hash tables lesson. Be sure to try and practice what you've learned by completing the practice exercises, and good luck.